A U.S. aircraft carrier does not stop operating because a storm forms. It carries more than 60 aircraft, worth billions of dollars, across open oceans where weather can turn violent within hours. Those jets sit on an exposed steel deck, hundreds of miles from land, while the ship continues its mission. Carriers operate in the Western Pacific during typhoon season. They cross the North Atlantic in winter storms. They patrol the Arabian Sea during monsoon cycles. These are not controlled environments. They are regions known for unstable and sometimes extreme weather. When winds rise and seas build, the ship moves. The deck tilts. Waves strike the bow and sweep across the surface. Every aircraft on that deck must remain fixed in place, despite forces strong enough to shift thousands of tons of steel. If even one jet breaks loose, the risk is immediate, not just to equipment, but to the carrier's ability to operate. The Navy understands this risk because it has seen what severe weather can do. In 1944, a powerful Pacific typhoon caught a U.S. fleet at sea. What happened during that storm changed how the Navy prepares its ships for heavy weather. The details matter, and we will come back to them. Understanding the risk explains why this matters. But risk alone does not protect anything. The real protection begins with how the flight deck is built. The protection of aircraft begins with the design of the flight deck. At first glance, the deck appears flat and open. In reality, it is a reinforced steel surface built to handle constant stress. It supports aircraft landings, jet exhaust, heavy towing equipment, and thousands of tons of moving weight. During violent weather, it must also act as a secure anchoring platform. Across the entire deck is a grid of embedded steel tie-down points. These are not random fixtures. They are welded into the ship's structure and spaced at regular intervals. Each point is designed to handle extreme tension loads. When an aircraft is parked on deck, heavy chains are attached from the landing gear and designated hardpoints on the aircraft to these tie-down fittings. A single jet is normally secured with multiple chains. In heavy weather, additional chains are added. The logic is simple. No single restraint is trusted. Each chain is tensioned manually. If the ship rolls, the weight of the aircraft shifts. That force transfers into the chains. The more severe the roll, the more force the chains must absorb. Redundancy prevents a single point failure from becoming a larger problem. Aircraft themselves are designed for carrier conditions. Carrier-based fighters have reinforced landing gear compared to land-based aircraft. Their structures are built to handle sudden vertical impacts during landings. That same structural strength helps them endure violent deck movement. The deck is also designed to manage water. It is not perfectly flat. It has slight contouring that allows water to move toward drainage channels. Along the edges are scuppers, openings that allow water to flow off the deck. Standing water increases risk. Proper drainage reduces the chance of aircraft movement. Below the flight deck is the hangar bay. This is an enclosed space inside the armored hull of the ship. When severe weather is expected and time allows, aircraft can be lowered into this protected area using deck elevators. Once inside, they are secured again. The hangar provides more shielding from wind, but it does not eliminate motion. The entire ship still moves with the sea. Securing procedures inside the hangar remain strict. The carrier's overall stability also plays a major role. A Nimitz-class or Ford-class carrier displaces over 100,000 tons of water. That mass provides natural resistance to rapid movement. The hull is wide, and the center of gravity is carefully managed. Ballast systems help maintain balance. Internal compartments can shift water weight to improve stability under certain conditions. The ship's design reduces excessive roll compared to smaller vessels. Still, size does not remove motion. In heavy seas, the deck can tilt several degrees in each direction. That tilt is enough to shift enormous force into securing systems. The structure is strong, but strength only works if it is used correctly. That is where preparation becomes critical. Long before a storm reaches the ship, the carrier strike group is already tracking it. Weather data comes from satellites, naval forecasting centers, and regional meteorological analysis. Storm paths are studied continuously. Command must decide whether to alter course, increase speed, or prepare to ride through the system. Avoidance is preferred when possible. But carriers operate based on mission requirements. They cannot always withdraw from an area simply because weather is approaching. When heavy seas become likely, preparation begins in stages. First, flight operations are adjusted. Aircraft scheduled for missions may be recovered early. Launch cycles stop. The focus shifts from combat operations to securing the deck. Every aircraft on the flight deck is evaluated. Some may be moved below into the hangar bay if time allows. Moving aircraft requires coordination. Tow tractors reposition jets carefully. Elevators lower them inside the ship. Once inside, they are secured again using chains and wheel chocks. Aircraft that remain on deck are treated differently as the risk level rises. Additional chains are attached. Control surfaces are locked. Canopies are secured. External equipment is checked to ensure nothing can detach in high wind. Fuel lines are inspected. The objective is to eliminate loose components. Chain tension is not estimated casually. Crews are trained to secure aircraft with proper load distribution. Chains must be tight enough to prevent slack, but not overstressed in a way that weakens them under dynamic force. After aircraft are secured, the ship transitions to stricter material conditions. Watertight doors are sealed. Non-essential openings are closed. Equipment is locked down. Internal compartments are prepared to contain flooding if necessary. The carrier also maneuvers strategically relative to wave direction. Taking waves at the correct angle reduces side-to-side roll. Heading directly into waves often provides greater stability than allowing waves to strike from the side. As conditions worsen, deck access is restricted. Only essential personnel remain topside. Safety lines are used. Movement becomes limited and controlled. The flight deck, normally active and crowded, becomes still. Throughout the storm, inspections continue as long as conditions allow. If a chain loosens or a restraint shifts, corrections are made when safe to do so. The crew does not assume that initial preparation is enough. Procedure is built on repetition and discipline. Every step has been practiced. But even with strict preparation, risk cannot be eliminated entirely. To understand that risk clearly, we need to look at where the system is most vulnerable and how small failures can grow under extreme motion. Behind every securing system is a crew that makes it work. A carrier has thousands of sailors on board. Among them are flight deck crews trained specifically to handle aircraft under difficult conditions. On deck, they are identified by color-coded jerseys that reflect their roles. Yellow jerseys direct aircraft movement. They guide pilots and control positioning on the flight deck. Blue jerseys handle aircraft chocking and chaining. They are responsible for securing jets to the deck. Green jerseys maintain equipment and operate catapults and arresting gear systems. Red jerseys manage ordnance and firefighting teams. Purple jerseys handle fuel. Each color represents a defined responsibility. During heavy weather preparation, coordination between these teams becomes critical. These sailors work in high wind, heavy spray, and unstable footing. The deck surface can become slick. Visibility can drop. Communication becomes harder as wind noise increases. Securing a fighter jet is physical work. Chains are heavy. They must be carried, attached, and tightened by hand. The attachment points are precise. Each chain must connect to the correct hardpoint on the landing gear or designated structure. Blue-shirted crew members handle most of this securing process. Yellow shirts ensure the aircraft is positioned correctly before chains are attached. Supervisors oversee the sequence to prevent mistakes. When the ship begins to move more aggressively, the work becomes more demanding. The deck may tilt. Equipment shifts slightly. Sailors must brace themselves while maintaining focus. The margin for error is small. If a chain is attached incorrectly, it may not bear load evenly. If it is left too loose, slack can develop when the ship rolls. That slack can allow the aircraft to shift before tension engages. Training reduces these risks. Flight deck crews drill repeatedly. They learn correct securing patterns for different aircraft types. They understand how wind direction affects exposed surfaces. They inspect their own work and the work of others. Supervisors verify securing points. Multiple layers of oversight exist. This is deliberate. The Navy does not rely on a single individual's judgment during heavy weather preparation. There is also psychological pressure. The value of the equipment is understood. Each jet represents years of engineering and millions of dollars. More importantly, those aircraft represent combat capability. Sailors securing jets know that improper preparation could damage not only hardware, but mission readiness. Work continues even when conditions are uncomfortable. But safety limits exist. If wind speeds exceed safe working thresholds, deck operations may be halted entirely. At that point, preparation must already be complete. The human factor is both a strength and a vulnerability. Training, discipline, and experience provide resilience. Fatigue, miscommunication, or rushed preparation introduce risk. Under normal conditions, the system is stable. Under violent weather, small mistakes can become amplified by motion and force. This leads directly to the core question of vulnerability. Where does the system rely most heavily on assumptions? And what happens if those assumptions are tested beyond design expectations? Despite its scale and preparation, the system has stress points. The first vulnerability is motion itself. A carrier's size provides stability, but it does not eliminate movement. In heavy seas, the ship can pitch forward and backward and roll side to side. Even a few degrees of roll can generate significant lateral force when applied to a 30-ton aircraft. When the ship tilts, gravity pulls the aircraft toward the lower side of the deck. The chains on that side absorb the load. If roll increases suddenly, the force on those chains multiplies. The system assumes that roll remains within predictable limits. If wave height exceeds forecast or wave timing becomes irregular, motion can become sharper and less predictable. The second vulnerability is cumulative stress. Chains are metal under tension. Repeated loading and unloading during prolonged storms creates fatigue. Even minor wear can weaken structural integrity over time if inspections are not thorough. For this reason, securing equipment is routinely checked and replaced as part of maintenance cycles. The third vulnerability is water. Although the deck is designed to drain efficiently, extreme sea states can push water across the surface faster than it can evacuate. Standing water reduces friction between tires and deck. If a chain were to loosen under those conditions, movement would accelerate. Another stress point involves aircraft elevators. The flight deck contains large platforms that lower aircraft into the hangar bay. When sealed, they are secure. However, they represent structural sections within the deck's surface. In extreme motion, any structural boundary requires careful monitoring. Human decision-making also remains a variable. Command must balance mission requirements with storm avoidance. Sometimes repositioning is limited by operational commitments. Remaining closer to a weather system may be necessary to maintain presence or support Allied forces. If preparation time is shortened due to rapid storm development, securing procedures must be executed faster. Speed increases risk. The most serious vulnerability is cascading failure. If one aircraft were to break free, its mass would allow it to strike adjacent jets. That impact could loosen additional chains. Fuel tanks could rupture. Debris could damage tie-down fittings. In extreme scenarios, fire risk increases. At that point, the deck becomes both a safety hazard and an operational liability. Flight operations would be suspended. Damage control teams would respond. The carrier's combat role would be reduced until repairs are made. This scenario is unlikely under proper preparation, but it is not impossible. The entire system is built to prevent that chain reaction. To understand why these precautions exist at such a strict level, it is useful to look at a historical moment when weather overwhelmed naval forces. In December 1944, the U.S. Third Fleet was operating in the Western Pacific during World War II. The fleet included aircraft carriers, cruisers, and destroyers. Weather forecasts at the time were limited compared to modern standards. A powerful typhoon formed and moved toward the fleet. The storm, later known as Typhoon Cobra, produced extreme winds and heavy seas. Several ships attempted to maneuver through the storm, but the scale and intensity were underestimated. 3 destroyers capsized. Nearly 800 sailors were lost. Aircraft on carrier decks were torn loose or damaged. Some were blown overboard. Flight decks were struck by heavy seas. Equipment shifted under violent motion. The carriers themselves survived, largely because of their size and structural strength. But the event exposed weaknesses in forecasting, storm avoidance doctrine, and preparation procedures. Investigations followed. The Navy reviewed command decisions, weather reporting systems, and securing methods. The conclusion was clear. Weather had been treated as a secondary factor compared to operational objectives. After Typhoon Cobra, improvements were implemented. Weather tracking capabilities were expanded. Meteorological analysis became more integrated into fleet operations. Storm avoidance became a more deliberate priority. Securing procedures were revised to account for extreme conditions. The understanding of dynamic load during heavy roll was improved. The lesson was not that carriers were fragile, it was that the ocean could impose forces beyond expectations. Modern carriers benefit from satellite forecasting, real-time storm tracking, and decades of operational refinement. Yet typhoons and hurricanes remain unpredictable systems. Their paths shift, their intensities change rapidly. In recent decades, carriers have continued operating in high-sea states. While catastrophic losses like 1944 have not repeated at the same scale, aircraft damage during heavy weather has occurred. Smaller support vessels remain especially vulnerable. The historical case reinforces a simple reality. Preparation must assume that forecasts can be wrong. Weather is not an enemy force. It does not adapt strategically, but its unpredictability can create operational strain equal to hostile action. Understanding this history explains why modern procedure appears cautious and layered. But beyond physical damage, there is another dimension to consider: the strategic effect if a carrier's air wing becomes temporarily compromised. An aircraft carrier is not just a ship, it is a signal. When a carrier operates near a contested region, it represents air power that can be deployed without relying on foreign bases. It carries strike aircraft, electronic warfare platforms, surveillance systems, and command capability. If violent weather damages multiple aircraft, the effect is immediate. Fewer jets available means fewer sorties. Reduced sortie generation lowers strike capacity. Air patrol coverage may shrink. Support missions may be delayed. In regions where tensions are already elevated, this reduction matters. Adversaries monitor carrier activity closely. Satellite imagery tracks deck configuration. Intelligence services estimate sortie rates. Changes in aircraft posture are noticed. If a carrier's air wing is partially disabled due to storm damage, even temporarily, that weakness may influence strategic calculations. Allies also pay attention. A carrier strike group is often deployed to reassure partners. Operational readiness reinforces credibility. If readiness drops, even briefly, it can affect diplomatic confidence. There is also scheduling impact. Carriers follow structured deployment cycles. Damage caused by severe weather can require unplanned maintenance. Repairs may need to be completed at port. That disrupts deployment timelines and readiness planning for other fleets. Financially, aircraft repairs can cost millions per unit depending on damage severity. Replacement parts, structural inspections, and flight recertification take time. Strategically, the most important factor is continuity. A carrier must remain capable even under environmental stress. If it can maintain operational aircraft through violent weather, it reinforces the message that presence will not be interrupted easily. This is why weather protection is treated as part of combat readiness, not separate from it. The objective is not simply to survive a storm, it is to emerge from it fully functional. When a carrier sails into high seas, the securing chains on the deck represent more than physical restraints. They protect strategic leverage. That leverage depends on engineering, procedure, discipline, and constant assessment of risk. Modern carriers are designed to endure extreme conditions. Their survival in heavy weather is not accidental. It is the result of layered systems built from historical lessons and operational experience. Yet the ocean remains unpredictable. The margin between stability and cascading failure is controlled through preparation and vigilance. In the end, protecting fighter jets in violent weather is about preserving the carrier's core purpose: sustained air power at sea.